Hello, everyone. Welcome to EPA's 18th Annual Drinking Water Workshop. We will begin in a few moments. In the meantime, please take a moment to respond to the poll that is about to be on your screen. Thank you. All right. Hello, everyone, and welcome to EPA's 18th Annual Drinking Water Workshop. We are glad you could be here virtually with us today for session T2. If you have not done so already, please take a moment to respond to the poll on your screen. If at any time during the webinar your screen does not load the next presenter's presentation, please try refreshing your browser. If that does not work, please try exiting full screen mode, or you can exit and rejoin the webinar. We are here to help, so at any time, feel free to use the questions box for any other technical issues. To get us started, let me run through a few quick questions, notes for the questions, excuse me. So I will run through quickly how to submit questions. When you see the chat button and go to webinar, you will type and submit your questions anytime. And then at the end of the webinar, we will take a chance to run through your questions and our presenters will be able to answer them. Next slide, please. Next slide. Great, so we have a bunch of really great presenters here today, and we have a great program. So I am going to read the bios of our 5 presenters. So first up, we have Tara Haxton, who has a BS in Civil Engineering from the Rose-Hulman Institute of Technology and an MS and PhD in Environmental Engineering from Vanderbilt University. Since joining EPA in 2007, Tara's research has focused on modeling the fate and transport of contaminants in drinking water distribution systems. Past research areas have included using modeling tools to help detect contamination, identify the source of contamination, determine grab sample locations to outline contaminated areas, and evaluate flushing strategies for contamination incidents. Her current research area is developing and applying modeling and simulation tools to assess the resilience of drinking water systems to disasters like earthquakes, power outages, pipe breaks, and the loss of source water. We are excited to have you today, Tara. Next up, we have Feng Chang, who received his bachelor's and master's degrees in environmental engineering from Tsinghua University in China. Feng completed his PhD at the University of Cincinnati in the environmental engineering program. After getting his PhD, Feng worked briefly as a postdoc for EPA, during which time he wrote the initial code for multiple species extension, MSX, to EPANET. Feng joined the engineering software company Innovise in 2008 and worked there as a principal software engineer in 2019. Feng joined EPA's Water Infrastructure Division as an environmental engineer in April 2019. His focus at EPA is on researching hydraulic and water quality issues in water infrastructure systems. Next up, we have Ben Burkhart, who received his bachelor's degree in mechanical engineering from the University of Cincinnati. Ben joined the EPA in 2020 as an ORAU contractor. Prior to joining the EPA, Ben spent his last 3 co-ops as Wayne Water Systems designing and testing residential water pumps. Ben's research at the EPA has focused on water age and EPANET. Ben provides technical support for EPANET, including responding to users' questions and producing presentations and papers to help EPANET be easier to learn and use. Next, we have Jonathan Burkhart, who earned his PhD, master's, and bachelor's degrees in chemical engineering from the University of Cincinnati. John joined the US EPA in 2013 as an ORISE postdoctoral fellow, and more permanently in 2015. John's research at EPA has focused on modeling contaminant fate and transport in water distribution systems, and more recently in premise plumbing systems. John has supported EPANET MSX, WNTR, and PPM tools development to support research related to these systems. John also leads research efforts associated with understanding water treatment with granular activated carbon. Please welcome, one more. Last but not least, we have Robert Janke, who earned his bachelor's degree in chemistry and a master's degree in health physics from the University of Cincinnati. Rob joined US EPA in 2003. Prior to joining EPA, Rob spent 12 years with the Department of Energy overseeing a large-scale remediation while focused on developing real-time radiological survey and instrumentation and procedures. Rob's research at EPA has focused on understanding and dealing with contaminant threats to drinking water distribution systems, TIVA-SPOT, and developing the tools for real-time modeling. Rob helped coordinate the establishment of EPANET RTX open source project that has helped lead to the community open source software project for EPANET. Thank you, and I'll turn it over to you.
Thank you, Katie. Hello, everyone, and again, welcome to this training session on EPANET. We like to call it, some folks call it EPANET, we often call it just EPANET. But here's a quick summary of our workshop today. It'll be structured into 2 parts. Part 1 will provide an overview and introduction to EPANET. Part 2 will consist of presenting and discussing 4 example EPANET applications that participants, that all of you can follow to get familiar with and use EPANET. The 4 applications will be in the form of exercises and will include building an EPANET model, performing a hydraulic simulation and using demand-dependent and pressure-dependent demands, performing a water age analysis, and performing a water quality chlorine analysis. Here's an outline for the workshop. We'll have this overview and introduction to EPANET to begin with, and Tara is going to lead that off, and she'll talk about the EPANET modeling capabilities and introduce some applications. Fong will take over and talk about model building, hydraulic modeling, water age modeling, and chlorine modeling. And then after lunch, we'll have a lunch break where we can help people get set up with EPANET if they are having trouble, or answer questions on the first part of this workshop, if there are any questions there. And then after lunch, we're going to have application sections that deal with these four applications of model building, hydraulic modeling, water age modeling, and chlorine modeling. Each application will begin with a little lecture, a few slides on the application. Then there'll be a demonstration of the application, and then it'll be a do-it-yourself exercise. So we hope you all enjoy this, and this will be, all these slides and everything, as well as the applications we'll make available after the workshop. So again, thanks again for attending, and I'm gonna at this point turn it over to Tara Haxon.
Hello all, thank you for coming today. I hope you are excited to learn a little bit of overview introduction to EPANET. Next slide. So what is EPANET? EPANET is not an acronym or nor initialism, and we prefer that it's an all caps designation. EPANET is a Microsoft Windows-based computer program that is for your desktop or laptop. EPA currently provides 3 versions of EPANET, a graphical user interface or GUI, a DOS command line, and a programmable toolkit for those that want to customize custom applications of EPANET. EPANET is used to model and analyze a drinking water distribution system. The input for EPANET is a drinking water distribution system model, so the pipe layout that you might be getting from a graphical user or GIS system, and the outputs could be the hydraulic and water quality parameters that provide information on the status of the drinking water distribution systems. For instance, the pipe flows, or the pressures in these pipes, and water quality such as the disinfectant concentrations or the water age. EPANET is an open source software that is free to use. Today's talk is going to focus on the GUI version of the software. Next slide, please. So a little bit of a knowledge check. So what does EPANET stand for? Great. The solution, hopefully everybody got that. It is not an acronym. The correct name is EPANET and is the name of the software and not an acronym. So moving on to describe a little bit more information about EPANET and how it works. So this is a drinking water system schematic here, and a typical drinking water system is composed of 4 main components: the source water, the treatment plant, the storage facilities, and the transmission mains, distribution system pipes, and the pumping facilities. So this is a schematic that looks at these different facilities that transport the water from the source to the treatment plant to the distribution system customers. EPANET models are generally constructed to represent the distribution system, basically from the treatment plant to the distribution system pipes to the customer meters. Next slide, please. To get started and acquainted with EPANET, we're going to go over some simple terms and definitions that are important to EPANET. So water distribution systems, or WDS, is a collection of pipes, tanks, pumps, valve control systems, and other components that work together to move and transport the water from the source or the treatment plant to the individual users or customer taps. Network file is either a text file that has an IMP extension or a binary file with a NET extension. This is what actually represents the water distribution system. It is a pipe network layout, basically the infrastructure map that includes those tanks, pumps, control systems for the valves, and other components that are needed to describe the water distribution system network itself. The hydraulic model is the actual network model that is simulated in the EPA for the hydraulic status. And then the water quality model is the network model that is simulated for water quality. Like in an actual water distribution system network, water enters from the reservoir or well, and then the customer's water demand drive the movement of the water through the distribution system. Next slide, please. There are 2 types of simulations that can be performed within EPANET, and these are steady state and extended period simulations. So a steady state simulation is a network analyzed as a snapshot in time, so time 0 in EPANET. And while an extended period simulation is a network that is analyzed over time. And we'll get into more details about these later in the presentation. Water distribution system modeling using EPANET is a process for gaining understanding of how a water distribution system is operated or can be designed and improved. Water distribution system modeling is a mathematical process. It uses formulas to convert the physical or infrastructural model into a form that is able to calculate the hydraulics and chemical properties of the water to represent the model behavior of the systems. So this is able to provide you information about what are the statuses of those properties of the hydraulics and water quality. Next slide, please. So there are multiple reasons why we suggest developing a model of your distribution system network system. So central to using EPANET or performing a water distribution model is the need for a model. So this is the motivation could include developing a model to perform planning exercises or capital improvements to better understand water usage and conservation needs, or best how to implement a tank or pipe replacement project. Motivation may be forming some needed design or maybe for better understanding of operations or how best to solve a particular operational problem. Now, in addition, you can look at designing facilities, different sizes that might be applicable if you're gaining more customers in your system, and also for firefighting analysis to make sure that you have the required demands at certain locations to be able to maintain the fighting capabilities. In addition, models can help you train operational staff or address hydraulic and water quality concerns or even in emergency situations. So water systems are complex operations involving many thousands of connected components that must work together to efficiently and reliably deliver high quality potable water to consumers. Understanding the processes and operations involved in this complex operations requires data and information and most notably a network model. So EPA can help you address these concerns. Next slide, please. So just to reiterate, EPANET is a software program that allows the user to easily perform hydraulic and water quality modeling. So the hydraulic modeling determines the hydraulic states of the system. So for instance, the flows, pressures, and tank levels of the system. It is able to evaluate the current operations and conditions and test the impacts of changing these different operations on these different components. You're able to design new water distribution system components or upgrade existing systems. Water quality modeling determines the chemical state or the water quality of the system. For instance, the water age, how long it's been since the water left the treatment plant to it arrives at its destination, or how to manage disinfectant levels in the system and make sure that you're getting the chlorine or disinfectant level that you want at a particular location. It also can be used to help model if there were to be a contamination incident, where would those contaminants travel, what would be the exposure to the consumers, and perform risk analysis. So EPANET offers a lot of variety of information for different purposes. Next slide, please. So a little bit of background and history of EPANET. EPANET was developed by Louis A. Rossman, who has been retired from the EPA since March of 2014, and he developed it at EPA in the early 1990s. The first non-beta release of EPANET was in 2000, which was version 2.00.00. The US EPA's latest reversion was 2.00, was in 2008 with the version 2.00.12. However, maintenance and advancements of EPANET is currently developed through community collaborations at this website here, which is Open Water Analytics on the GitHub site. The US EPA's latest version is 2.2.0, and this was developed and made possible the community collaborations with Open Water Analytics. Next slide, please. So there are improvements to talk that have been made to the EPANET since the version was released. So here in 2.2, we're going to highlight some of the improvements that were included. Some of the abilities that were added were the ability to use pressure-dependent demands in the hydraulic analysis. And Fong will talk later more about the importance of this in the next couple of slides. Other important improvements include robust handling of zero and low flow conditions, which might be important if you're having these systems in your, or those components in your system. It also has the option to allow tanks to overflow. It also has improved the mass balance results for water quality analysis and other being able to have faster solution times. And again, it has enhanced an application programming interface function library or an API for customized EPANET. And you can learn more about that on the Open Water Analytics page. Next slide, please. So a little bit more detail about where to get and download EPANET. So specifically the graphical user interface that we're talking about today. So you have two places that you can go to. You can go to the US EPA's website, which is listed here. Basically, www.epa.gov/water-research-EPANet, or you can go to our US EPA's GitHub site that has a repository for specifically the 2.2 release, and the link is provided here for your reference. So on the website itself, there are information about the software, the GUI itself, and there is 2 different versions of that GUI version. There is a self-extraction installation program, and it is using an exe file that is installed there. So this is kind of a version that requires administrative privileges to install. There is also a non-installing version for EPANet, and you can use a zip file for that. And that basically has all the same information that the installed version, but does not require administrative rights. Also on the website is our user manual. We have a PDF version that people can download, and we also have an online version through the Read the Docs application, in which allows you to, quickly reference things and search online the different versions. On the EPA's GitHub site for the 2.2 release is basically a mirror image of the website information, but it allows us to easily maintain and keep the updated information on that website, on the GitHub site. We like to recommend people to go to the GitHub site for the latest information on where we can, since we're able to maintain and update it easier. Next slide, please. So installing and running EPANet. If you have elevated privileges, you can use the self-extraction installation program for EPANet 2.2, which will be the EPANet 2.2_setup.exe file. And again, it requires administrative privileges. It installs EPANet program itself, help files, tutorials, and release notes in a Microsoft Windows Start menu. So you're able to go to your Start menu on Windows and pull up these different files. It does install example files, but it might be hard to find these on your folders just because of the way that Windows sometimes installs things. So we provide an example here that it could be placed in a subfolder named EPANet projects / examples in your documents folder. So if you have trouble finding this example files, please reach out to us and we can help you the best that we can to determine where this was installed on your system. Next slide, please. So for this tutorial and workshop today, we're recommending running the EPANet non-installing version. And so this is the non-installing version of EPANet, is an EPANet.2.2 zip file. And everything that is included with the installation version is included with the zip file version. And it can be saved anywhere on your computer. It runs EPANet through this EPANet2w.exe file that is highlighted here in the screen capture below. We also include the DOS command line interface for EPANet, which is the run EPANet.exe file. And again, this option does not require administrative privileges to use. Next slide, please. We also wanted to highlight some resources that are available if you ever have any questions about EPANet beyond this introductory training materials that we're providing here today. So for general information about EPANet, you can go to our US EPA website, as we mentioned before, or you can email us at questions@epanet@epa.gov. We also have the EPANet GitHub repository, which has information about the general use and the interface. We also have an EPANet community that is supported at the Open Water Analytics, and so you can ask information about the hydraulic and water quality engines there. There's also community forums, so you can reach out and ask the community any questions that you might have to ask. And again, if you want to contribute to the development of EPANet, there is this website there that on the Open Water Analytics GitHub site, which has EPANet issues, and then you can provide any issues that you want to see in future enhancements to EPANet. So we want to make sure and encourage everyone to reach out to us any of these through mechanisms that we can help you and address any comments or questions that you have about the use of EPANet. Next slide, please. So this is our second knowledge check. So if you have questions about EPANet, where can you find your answers? Well, thank you for responding. I hope that everybody was able to respond with E, all of the above, because these are all opportunities and ways to reach out to us through the integrated help feature of EPANET, emailing us at epanet.gov, the user manuals FAQ section, or ask the ASDWA community on help for GitHub. Next slide, please. So now I'm going to provide a very quick overview of the hydraulics review of how EPANET focuses or functions in this regard. So 4 basic assumptions are about how EPANET calculates flow. First of all, flows are all incompressible fluids and liquids. Flows can be turbulent, laminar, or transition flows. That all pipes are closed with no added volume. So contaminants are injected as modeled as mass per time, and that all pipes are modeled as full. So there's no partially full or intermittent flows cannot be modeled with EPANET. And for more background and supporting information and review the basic principles of using hydraulic models, we reference these 2 books, the Advanced Water Distribution Modeling and Management book by Hayes Methods, and the Water Distribution Systems Handbook with the editor Larry Mays. So these are good references for everybody to learn more about this. Next slide, please. I just wanted to give some brief introduction to the EPANET units. So EPANET can support both US and metric unit systems. So customary US customary systems usually are gallons per minute or GPM or millions gallons per day MGD. So you can have the information there about how to convert those. It also has SI units, so like liters per second or cubic meters per second. And EPANET supports both these units. And you can change these as you can see here in these screen schematics of using the help menu to select what kind of units there are, and then you can pull down in your EPANET solutions and pick out which kind of units you want to use. Next slide, please. So continuing on with the units and the components within EPANET, the pressures can be either US or metric, so pounds per square inch or Pascal for metric, depending on what you've chosen for flow units. And then normal operating ranges of pressures in drinking water systems are basically around 20 psi for minimum and or US units, and maybe 80 to 100 psi in maximum, depending on how the system is operated. These are again just general operating procedures, but could be different for each system. And so a little bit more about the components and how we call them within EPANET. There are nodes in the system in EPANET, and these represent junctions, tanks, and reservoirs. And please note that reservoirs are nodes with infinite internal sink or sources of the water. So this is basically where you would model information about your treatment plant. You would typically use a reservoir for that. Links are another component of in EPANET, and these include pipes, pumps, and control valves. And links must have both a start and end node. Pumps and valves are modeled with 0 volume, so basically they're just basically a connection between 2 nodes, but they have no volume associated with them. And so that's just more an implication. If you have any questions, please reach out to us. Next slide, please. So let's get started with EPANET and learning more about how to open it and work with it. So we recommend that there are 3 easy ways to get started with EPANET. One is to use the HTML-based tutorial and the integrated help files. You can access the help from the start menu, or if you had done the self-installing version, or if you had done the non-installing version, you can extract the HTML files from the menu bar help and help topics. The quick start tutorial provides a quick and easy way to get familiar with EPANET. The tutorial will walk you through installing EPANET, or if you had used the non-install version, setting up a project, constructing the EPANET example network, setting the object properties, and saving and running both a steady state and extended period analysis. We'll go in more details about these later. The second approach is just to open the user manual, read and experiment with EPANET. And again, don't be afraid if you will break it. You know, this is common things to way to just get familiar with tools. It's just to use a user manual and learn from there. The third approach is to load one of the example networks that is provided with EPANET and experiment with them. You can again refer to the user manual or the integrated help if you get stuck, or always reach out to us if you have questions, or even the user community on that Open Water Analytics GitHub site. Next slide, please. So this is just to get you a little bit more familiar with the EPANET's workspace. So in the EPANET's GUI, at the top you'll have a menu bar, a toolbar, you'll have a network map, a project browser, and a property editor. And these are highlighted here for you for reference. You can also refer to Chapter 4 of the user manual for a detailed discussion of what the EPANET's workspace looks like. And then the following slides, I'll provide a quick overview of some of these screens. And don't forget, if you get stuck, you can use the integrated help within the tool itself by using menu bar help or help topics, or you can just press F1 to easily access the help. Next slide, please. So a little bit more detail of information about the menu bar options. So at the top of the screen, there's a menu bar that are under the options that are there. So moving from left to right on the menu bar, you have a preferences, which allows the user to get some general or to set some general and format preferences. Although not shown here, the formats preference screen allows the user to set the number of decimal places that is shown in the results for node and link parameters. You'll find this important for reviewing your simulation results and animation. The next option on the toolbar, or the menu bar, excuse me, is options. And this allows the user to set the map view options for the network model. So you're able to change different parameter sizes in terms of what size the nodes or links show up, maybe how they're proportionally, if you have some value plotted on them, the size is proportional to what that value is. You can put different flow diagrams on there in terms of what the direction of the flow is moving in the system. So it allows you to customize the map for your purposes. The next option is the project summary, which provides a summary description of the network's model's characteristics. For example, how many pumps are in the system, how many nodes are in the system, etc. It just gives you a quick overview of that. And you can edit and provide information about what you're going to call the file if you were to save it in terms of the description of in the file. Another menu bar option is the calibration data, and this allows the upload of data or in a text file format containing calibration data for the network file. So each line of the text file would contain a location ID, a time of the measurement, and a value. So for instance, if you had specific information about what would be a disinfection or chlorine residual sampling, you can upload this calibration, and then you can match that data to your simulation data to see how far you all are off. And the last option on the menu bar is the defaults. It allows the users to edit their default properties, and the defaults make it easier and faster to build models in the future. So you can check this option if you want to make more models in the future have the same characteristics. We'll be going more detail about all these options in the future tutorial sections. Next slide, please. Moving on to the toolbar, that's just part of your GUI application. So by default, the toolbar and are located next to each other, but you can obviously move them, arrange them, or hide them as necessary. The standard toolbar has your common buttons that you're used to for any kind of Word or Office products, right? You have the new, open, save, print, and then you also have options about copying, deleting, and finding if you want to find a specific item in your network map. There's also the run, be able to run the simulation. And then once you run it, then you have options to query the data, graph it, tables, and other options. The map toolbar has buttons for manipulating the network map view and buttons to add new components to the network model. So again, you can select different components of the model. You can pan around the map, look at different things. You can zoom in. Then you can add the different components of the junctions, reservoirs, tanks, etc. And we'll be going into more detail about this later. Next slide, please. So the network map section of your GUI interface displays schematics of the diagram of your objects of the water distribution system network model. So that's the number one here. So that's where you can build your network model in the network map. And And then you also can use it to run and graph your simulation results. So once you have created the model and then you run a simulation, you can view the results of that simulation on the network map as well. And this can be a time sync animation or just on the map, or you can also use the graphical tabular forms to create graphs or plots of the results in your network map view. Again, we'll be showing you more specific applications of this later. Next slide, please. The next component in your GUI interface is the project browser. It has two tabs. One tab is the data browser and the other is the map browser. The data browser, allows a user to access native network model components by category and then open them into a property editor. At the bottom of the browser data are options to add, delete, or edit objects. So you can click on the data browser and open up specific components. Like if you wanted to open up here, junction 23, you can open it up and see all the properties of junction 3 and edit it. The map browser on the other tab allows the user to navigate an animation that is select parameters from the drop-down boxes for nodes and links, and then the time of simulation to be viewed in the network map, and then start and stopping animations. So for this little diagram here, we have chosen to have the chlorine results modeled on the nodes, and then the flow modeled on for the links. And then here we're just simulating time step 6 hours, and then you can press the play button as necessary to see the animation flow through time. You'll see more of the details later of these applications. Next slide, please. As I briefly mentioned, when you double click on the data browser, you're able to collect different properties of the network model. And for instance, the property editor would come up. So this is junction 10, and the property editor will look different depending on what kind of component you selected in the data browser. So you can edit the network model components here, and it's either they're the starred items or kind of the things that are required for that option, and the yellow ones in this depiction here are the ones that are calculated from the simulation. So they're currently NA because they have not run the simulation. Some of the other values you can add in, but they are not required if they don't have the star. Next slide, please. So here's some more information about that component's properties. So again, if you double click the component and the properties window comes up, the star are the required ones. So here we have highlighted some of the required ones for each of the different network component types, so you can see what they are. And then the blue are the ones that are not required but are commonly used. So examples are for the junctions, you can need to provide the elevation, but commonly people provide some base demand or a pattern associated with that. And so here's just highlighting some of those that might be useful to get your simulation started. And as you learn more through these tutorial applications today, you'll understand kind of values and information you can provide in there. Next slide, please. So the knowledge check. What part of the EPANET workspace would you use to view simulation results? Great. Well, I hope that you all answered the network map, since it's used to view, build, modify models, as well as view the simulation results and animate it. So next slide, please. And I believe that I will be turning it over to my colleague Feng Sheng to talk to you some more. Thank you for your time.
Can anybody see my slides?
You look great, Feng.
All right. I'm going to talk about EPANET, the modeling capability. Basically, it's hydraulic and water quality modeling capability. First of all, EPANET model can be, of course, very complicated, but it can be extremely simple. So you can build a very simple network by adding a reservoir with enough high elevation. Then you add one junction and assign some demand, and you connect these two nodes with a pipe, and you can run the simulation. You can see the hydraulics results. You can see the flow in the pipe. You can see the head at the junction. Today, I'm not going to demo how to use EPANET, because in the afternoon session, Ben Burkhardt will walk you guys through 4 examples and give very detailed instruction on how to use EPANET, build a model, and run analysis. First of all, we talk about the hydraulic. Yes, EPA model hydraulics condition over one period or multiple periods. As Tara mentioned, you can do one snapshot analysis. Usually people do this kind of analysis to see if water demand can be met. But now people more and more often doing multiple periods simulation. I should note that there is no transit or water hammer analysis incorporated into EPANET. EPANET is doing one or multiple, basically, steady state analysis for the distribution system. Transient analysis is different because it need to solve transient equations, so it's not incorporated into EPANET. Lots of commercial softwares, company like Bentley or Innovise provide transient analysis. And I know UT Austin, they develop open source transient analysis package too. So, but EPANET doesn't include any transient capability for now. For any EPANET network model, demands has to be assigned. We need to know how much demands are consumed at each junction. Some junction can have 0 demand, but we must have sensor data, water consumption data in order to build a hydraulic model. Links in the EPANET include pipes, pumps, and valves. They basically transfer water from source to consumer nodes. For steady state analysis, again, it's a snapshot analysis. You give a fixed demand. You can see if the water pressure is enough. For example, you can do some very simple hydraulic analysis. For fire flow, so you assign a huge demand. Let's see if we have enough water head or water pressure for this kind of fire flow situation. More often, people use extended period simulation. In this kind of simulation, demand can be changed, and the simulation is basically a series of steady state analysis, a series of snapshot analysis. Again, it's not transient analysis; it's a sequence of steady state analysis. Typically, people use this EPS to simulate peak days, for example, in summer when the water demand is high. So people can, planners can see if their system can provide enough pressure to meet this kind of high demand in summer. Why it's not responding? Yeah, for any hydraulic models, there is all kinds of hydraulic factors you need to input into the distribution system network, include demands, dynamic head, elevation, pattern, and controls. Basically tells how it should be operated. We will go into details about patterns and control, and also about pipe properties. We need to assign diameter, length, roughness to the pipes. And other than pipes, we also have like pumps and valves. We need to specify pump curve, control valve settings. And we know in distribution system, tanks play a major role in order to provide a robust supply. So tank size, tank elevation, initial level, all this kind of information need to be specified for tanks. And we also have like a minor loss coefficient to accurately calculate the head loss in the system. And now let's talk about extended period simulation. In order to do extended period simulation, we need to have demand pattern. So usually pattern time step can be 1 or 2 hours, but it can be very small. For example, 1 minute to do very detailed hydraulic. Each node, basically consumer junction, has its own base demand. Base demand is usually the average demand. So you can calculate what's the average demand for this node. This node can be a house, it can be a community, large or small. So depending on the scale of your network model. Multipliers can apply to the junction's base demand so that you can calculate the instant demand. So usually the pattern value is very high in like 8 a.m. or 7 p.m. when people use a lot of water. It can be very low, like probably 0.2 during midnight. So basically, pattern plus base demand can help people model the real dynamic demands in the system. Also, one pattern can be set applied to multiple nodes. Multiple nodes can have the same pattern because in order to build a very detailed model, lots of information are needed. So at the start, probably we only have a couple of patterns to model the demand, but when we get more and more information, each node can have its own pattern. So basically, pattern can not only model demand, but also model like reservoir head change or energy price of the pump. So pattern basically is used to simulate the changes over time. It can repeat for a certain period. Usually it's 1 day. I saw people using pattern to model 1 week situation. So basically things repeat day after day or week after week, but it's a flexible setting. You can set any kind of pattern repeat period. This is a typical kind of pattern for demand. You can see the water demand goes up and goes down for 24 hours period, and each pattern value is 2 hours here. More often, probably now is 1 hour or even half hour because model become more and more detailed, and all pipes model are normal now. So the pattern steps getting smaller. That's what I saw in the practice. These 2 nodes, node 13, node 23, basically they have different demand or different average demand. They share the same pattern. So you can see they go up at the same time, go down, and go up. And this is their pattern. The base demand, so that's why their demand. For extended period simulation, you can run it. It's relatively fast, the hydraulic simulation. And then lots of people care a lot about node pressure because they want to make sure the PSI is high enough for their system. So you can see it. Again, you can plot 2 nodes, results, and you can see the pressure goes up. Again, this system is 24 hours pattern period, so everything repeats 24 hours. If you set the pattern period to be 1 week, the hydrolysis will repeat every 1 week. Then we can see, you can also see the tank operation. Tank level here going up, meaning the tank is filling basically the treatment plant is pumping water into the tank. Likely during time when the energy price is low. Then when energy price is high, the system can use the tank to drain the water into the system. So you can see the tank operation here. And also, because in that example, and we'll probably show you the network in the EPANET distribution. You can also see the pump operation. We can see here the pump is off. And when we go back, this off time corresponding to the tank draining time. So when the pump is off, the system is provided by the tank. And when the tank is on, when the pump is on, the water the tank got filled. So basically, you can run EPS simulation, see how a system work hydraulically during 1 day or 1 week period of time. And also, you need to assign demands. The more accurate the demands, the more accurate the model input. Of course, you get more accurate system operation conditions. Then we will talk about the EPANET. Before the EPANET 2.2, people very often, especially for large network modeler, they will see negative pressure warnings. In reality, because we are doing EPS simulation, we are not doing transient analysis, we shouldn't see negative pressure. Why? Because the assigned demand cannot be provided without negative pressure. So the simulation, the engine find the negative pressure so that the head is high enough to provide the demand, but it's not physical. So in EPANET 2.2, pressure-dependent analysis is introduced. Pressure-dependent analysis has been studied by many researchers in the past probably 2 decades. So it's a well-researched topic, but it's now finally be brought into EPANET. So user can assign demand, but the demand is met only when the pressure is high enough. So basically, you specify a required pressure. When the simulated pressure is higher than the required pressure, the demand will be provided fully. But when the pressure is lower than the required demand, the actual demand will be lower than the assigned demand. So basically, it's kind of reflecting reality. When you don't have high enough pressure, your water is not fully provided. So that's what we experience in reality. When the pressure is too low, of course, there will be no flow coming out of the turbine. So that's basically, it's called a pressure dependent analysis. Before, we call the demand dependent analysis. So this now is a option here. So in the data browser, as Tara introduced briefly, if you go to the option, hydraulics demand model, you can choose demand dependent model or pressure dependent model. And you can specify parameters. Basically, this equation is widely used as an equation to calculate the pressure, to calculate demand when pressure is not high enough. So here we have an interesting parameter K. Usually it's set to be 0.5, but in reality, it's not. And in EPA, we are doing lab research to figure out what is the accurate model for this pressure-dependent demand for different kinds of fixtures. So toilet, faucet, different. We find that it may be quite different, this K value is. So there is lots of research going on in this area, especially for press pumping system. You can see here is a result. So basically the demand here is 25, 25, 25 are all assigned demand. And here for junction 9, if we need, this is without pressure dependent demand. So 75 liter per second demand need to be met only with negative pressure. But here we can see in reality is probably more closer to reality than the left results. Only 61 liter per second demand water flow can be provided with a very low positive pressure. Pressure analysis is probably people most care about. There are all kinds of other hydraulic modeling functionalities built in EPANET. Controls, we can tell people how the system should be operated by providing simple or rule-based control. I would think the control can be quite complicated. So for first-time users, I don't encourage people to try controls. But in real network, and the network model I saw built by real utility engineers, there are lots of control. Some are very complicated. Also, we can have, define pump. So we can provide pump curves in EPANET, and we can do energy analysis, efficiency analysis. And we also can set a pump speed for different kind of pumps. There are like six types of valves, control valves. You can specify in the for the distribution network. I see a lot of pressure relief valve or pressure sustain valve, and in commercial software they also can have VSP, the speed pump. So it's kind of also more advanced simulation needed. But again, yeah, these pumps and valves can get quite complicated too in modeling. Yeah, here is a screenshot about simple control. It's quite simple. I will talk about it in the next slide. And the energy report, you can see, you can specify the energy price pattern, and you run the simulation based on how much head the pump needs to provide. It can calculate the total cost of energy for the system. Another knowledge check. Which of these can EPANET not do? A, steady state analysis, B, transient, C, extended period simulation, D, EPANET can do all of these. Straightforward. Can I go on, or people still answering?
Yes, you can go on. Thank you for everyone that answered.
Well, little bit surprised. I think I didn't do very good job. Yeah, EPANET cannot do transient state simulations. So it's always a steady state or called a steady state. So some people, yeah, especially people care lots about plumbing. Probably they got disappointed because transient analysis or water hammer analysis is very important for many hydraulic. All right. Then we talk a little bit more, extend a little bit more on controls. Controls basically are statements, are text statements that determine how the network is operated over time. It can be simple or rule-based. Simple one is quite simple. I think, yeah, if you want to really try to play control, then a simple control probably is where you should start. provide a link, pipe, pump, valve, and you give the link ID, and you tell the status. The status can be open, closed, or it can be pump speed setting for pump and the control valve setting for valve. So basically, then you tell the model when this status change should happen. Basically, if. So in the previous example, I kind of show the pump. Here is a pump, basically link 9 is a pump. It's open and closed based on the tank level. So when the tank level is low, the pump will be opened. When the tank level is high enough, the pump is closed. So basically the tank does not need water to be filled anymore. So it's quite straightforward. Again, the condition can be level in the tank, as shown in this example. It can also be pressure. Like if the pressure is low enough, you do something. And it can be time. The pump turn on in the middle of night and off in the afternoon. It can also be a quite reasonable control, simple control. Rule-based control is a little bit complicated. So basically, it's a combination of logic operation. So you use if, then, and, or, and you set a priority. Here you define. Here you can see two rules. One is if the tank level above something, then pump is on, is closed, and the pipe is open. So you can have a combination of conditions, and it can get really complicated. I saw rule-based control with hundreds of lines from some utility models, and sometimes it will give you unexpected results. So I think rule-based control is probably only for very experienced network modelers, but not for the beginners. Okay, we talk about hydraulics, and from EPA point of view, water quality is probably more important than hydraulics. In environmental engineering point of view, EPANET water quality modeling capability is quite powerful in some very reasonably simple way. I should put it this way. But it can only model one species. It cannot model interactive reactions between multiple chemical biological species. But it's still very powerful. We can first do water age analysis, and we can do tracing analysis. We can find out where the water comes from, and we can do chemical analysis. Of course, most commonly chlorine decay. So in this browser, you can see in the quality option you can choose. You can turn off the water quality option, so you only run hydraulics, very pretty fast hydraulic simulation. You can choose trace, age, or chemical. If you want to do chlorine decay, certainly you will choose chemical, or you can change it to chlorine, I guess, in the browser. It needs relative diffusivity, and the trace node, of course, only apply when you choose trace. And the quality tolerance is basically some model, what we call modeling tolerance. The less the tolerance value, the modeling should be more accurate for sure, but it takes more time. Normally, water quality simulation is much slower than hydraulic simulation. So that's why for large models, sometimes you just turn off the water quality and to see the hydraulics performance of your system first. Water age. Water age is a quite direct indication of water quality. You don't need to know too much about the chemicals. You don't need to know any chemicals. And of course, common sense told me the more water stay in the system, the more likely water quality. So it's like here, usually the larger the water age value, the smaller the chlorine residue can be. So water age analysis is always a favorite of me because if we don't know too much about a chemical reaction, we can use water age as a surrogate. Yeah, water age represents the time what has been stayed banned in the distribution system after leaving the source until it's consumed. Water age is frequently used as a surrogate for water quality. New water, we say, oh, it's good water, it's fresh water. Old water, we say, probably it's likely. And age, water age is influenced by residence time in tanks and travel time through the pipes. So typically, that's why it's typically water age high in dead ends or downstream a tank or a node far away from distribution system. We did some like physical tracer study and modeling. We find that the water age can be as high as 1 week in some systems with large tanks. So if we think about the water you drink 6 days old, I don't know how people feel about it. In order to do good water quality modeling, tank mixing is very important. Of course, tank mixing can be very complicated, and people have been using computational fluid dynamics to study the tank. But EPANET is a network model, so we cannot do too much computational time on tank mixing. There are 4 choices. Mixing model in EPANET, completely mixing. Of course, it's quite commonly used. And a 2-compartment. So basically 2-compartment is on the right side of the slide. It has 2 zones. One is the inlet outlet zone, one is the main zone. Both of the zones are completely mixed. So the water will be drawn from the inlet outlet zone first, then the main zone. And another 2 plug flow model, first in, first out, last in, first out. So there are 4 types of model. Most commonly, I saw people just use the completely mixing tanks. Probably they don't know, they don't really know what the mixing type they should use. So I think there is a lots of study can be done in mixing model or mixing mechanism of the water tanks in order to improve water quality. Yeah, it can be close, but probably none of them are perfect match for your system. Water age, you can see here there are 2 nodes. I don't know, it's here, node 26 is a tank. Node 25 is a node out of the tank. So when you run a simulation, if the tank turnover pretty bad, you can see the water age keep climbing up. So it's getting older and older in the tank. And the node out of the tank, when it receive tank of water, the water age, of course, is also very high. And when the tank is filling, the water pass that node and enter into the tank. So then this node receive fresh water. So for this node, people getting older, fresh, older, fresh, older, fresh water all the time. Ben Burkhardt made this heat map quite nicely. I never done that. So that's why it need a relatively complicated model here. Otherwise, the simple example network model don't have enough nodes to make up. So we have 2 water sources here. One I think is a reservoir, the other is a negative demand node, meaning the system receiving water from another seller. And you can see the water age closing to the water sources. Water are fresh, far away, water is old. That's all kind of engineering and common sense. And we do the trace. Yeah, he did this. Yeah, the trace. We pick a tank. If a node receive lots of water from the tank here, water kind of is bad. So usually tank water is old. So tank operation is very important. to make sure the turnover rate is high enough to prevent water age keep going up, you know. But of course, we know tank serves another important purpose is for the robustness or redundancy of the system. So if the tank is too small, the system maybe is vulnerable hydraulically. So balanced hydraulic and water quality concerns is an important topic research and engineering need to consider. We know there are lots of systems have multiple water sources. In California, I think this was originally from some California system, have surface water river sources, and this is lake sources, sometimes have groundwater sources, so have multiple sources. So one interesting thing is for the consumer, where my water come from. So in order to do this, you do tracer analysis, one of the water quality simulation option in EPANET. You specify a tracer node, you run once, you know, you specify another tracer node, you run, you know where the water comes from. So here you can see, here is receiving, here we do trace lake is here, okay? So in this yellow, like a majority is from lake. Yeah, it makes sense, it's close to lake, but also it receives some water from the river. And here, does this node close to the river, they receive zero lake water. Of course, this kind of map changes dynamically because at 1 o'clock, you receive probably 50% from river, 50% from lake, but at night, probably receive 30% from lake, 70% from. It's dynamic. So using water quality simulation tracer analysis, you can know where water come from. It's quite important because the water quality parameters can be quite different in different sources. So knowing the contribution, it helps sometimes analyze water quality problem consumer. Again, it's the result. Rather than showing the map, you can plot in a graph. You can see Trace river for node 175, Trace lake for node 157, sorry. So basically you run twice. One tracer analysis with trace node river. One trace analysis with tracer node lake. Then you plot the two. They should add to be 100. So like here 100, 0, like here 7, yeah, probably 90 something, but sometimes initial condition plays in. So usually sometimes you don't get a perfect 100% sum up during the initial period because initial water came from some tank in the system, not completely from these two sources. So if you see the sum adds up to be less than 100, it's possible from modeling point of view. Okay, another knowledge check. Which of the following best explain what EPANET tracer test is? Well, I think I need to do some reflection about next year's presentation, because tracer analysis, tracer test in EPANET is water quality simulation. It's not hydraulic simulation. But I think the question, maybe the wording has some problem, so we need to work hard on the wording of the question, I guess. But a tracer test is basically a water quality analysis. Water age, tracer, and the chemical are three options in water quality simulation. I didn't mention non-reactive chemical. Yeah, that's probably my mistake. So basically, when you do tracer, you don't model reaction at all. And it can track the proportion of water coming from every source. So it's water quality simulation. It's not hydraulic simulation. Sorry. Yeah, I think we need to spend some effort to phrasing these questions. Okay, last but not least, chlorine modeling, or chlorine is the most common water quality constituent modeled. So basically, we need to predict chlorine residue. Oh, now people use more and more often use chromium. Anyway, it's quite important in distribution system water quality. Chlorine and the chlorine residue can vary significantly during the day. Here is basically a graph. Looks quite complicated. The reaction between hypochlorite and natural organic matter. It generates disinfectant byproducts. And on the wall, the actual CL serves an oxidizer, for some corrosion or whatever reaction on the wall. KB means reaction in the bulk. KW means the reaction in the wall, on the wall. It can be quite complicated, especially if you think about chromium and how complicated the chemical reaction is. But EPANET is not trying to really physically model this kind of process. It's probably likely the job of EPANET multi-species extension. EPANET simplified the reaction and using only one single species, basically disinfectant, to model the process. And usually it can be modeled as a first order decay. And chlorine decay, basically it's a quite simple first order ordinary differential equation, dc dt to equal kc. And here the k, sorry, there's some mistake here, it should be. And this k is negative value, meaning it's decay rather than its growth. So, and the decay coefficient usually can be determined with a bottle test. So in utility, you set up a lab, you basically sample the water with all kinds of bottles, and you measure the chlorine decay, chlorine concentration over time. Then you do the curve fitting. You get first order decay coefficient. Likely, first order decay is not what your data tell you. Then you can do second order or zero order to see what happened. If none of them work, probably this single species model is not a fit. So we need to think about it more advanced. But usually people in reality, they just use the first order model. Even the model doesn't fit their data set well because it's built in EPANET, it's convenient to use. And decay can happen in bulk and on the wall. So in the bulk decay, again, it's first order decay. And typically, value is between -0.2 to 1.0 per day. Correspondingly, it half-life of the chlorine or disinfectant is 3.5 to 0.7. So again, it can vary greatly depending on your source water characteristics and your treatment process. But bulk decay is relatively easy to determine. Wall decay is more complicated because it happens on the wall and you couldn't see it. It's buried under the ground, and it's caused by corrosion. It's caused by biofilm reaction. It very likely depends on the pipe material, how old your pipe is. So this can be quite complicated. So it cannot be measured directly. So field studies probably needed to calibrate this water decay coefficient, or people choose from literature values, PVC or cast iron pipes, or corresponding pipe roughness to water decay coefficient. Again, it's quite complicated. In reality, I don't know how many people have really do field study and calibration to understand the water decay in their system. And but one thing for in EPANET you can see is basically chemical reaction analysis. It can tell you where the chemical are, for our case, most likely. In this model, you set wall coefficient to be 0, basically no reaction on the wall. Then you set up your first order reaction model for bulk flowing water, and you have a minus 0.5 per day decay coefficient because it's decay, so we have a negative value here. Then you can run the simulation for 1 day or 1 week. Then you can see how much water is lost. You see here, not water, sorry, disinfectant or chemical is consumed. You can see here, we must have a very large tank because lots of disinfectant get consumed in the tanks because lots of water are sitting in the tanks for a long time. And but here there is no wall reaction. Then you can play around, you specify some wall coefficient. You can see the reaction now is different. So 50% got lost. Tanks, 39 on the wall, only a small fraction in the bulk. Again, it's highly hypothetical situation. In reality, you need to figure out the bulk decay coefficient, the wall decay coefficient, and the tank size, and you run it, you can see it. And the large consumption of chlorine inside the tanks probably is not a very economical approach to maintain water quality. Probably meaning that the resident time of the tank is too high. Okay, I guess this is the last. This is there is no correct answer. Basically, based on your operation and based on your understanding, what chlorine is most. So I think everybody have different answers. Yeah, I think it's probably not very fair to put A as an option here because, yeah, we talk about water distribution system and treatment plants. Yeah, okay, yeah. Probably in the future we only have 3 options. Well, lots of people choose tanks. Yeah, probably it is the case, but I don't know enough from practice point of view. So if really lots of chlorine disinfectant is consumed in tanks, so we maybe think about it how to maintain tank quality in general, water quality in the distribution system through tank operation or boost chlorination. Okay, lunch break. That's good. So it's 12:25. Yeah, I think plan to finish this at 12:30. I'm glad I'm here. So you guys have 35 minutes, I think. Thank you.
Thank you all. We will resume at 1 p.m. Enjoy your lunch.
Okay, it's 1 o'clock now. We'll resume in a minute. We'll give everyone a chance to get back from their lunch and join us. Okay, hello everyone. Welcome back from lunch. Hopefully everyone has EPANET downloaded and operational by now. This is the first hands-on application today, and it will cover how to build a model in EPANET. It will be structured a bit differently than the other exercises. This whole section is a step-by-step tutorial, so you'll follow the videos in EPANET as I play them. For the future applications, it's separated into sections of I demonstrate how to do everything, and afterwards you try to do it yourself as an exercise. So again, if you want to do the hands-on exercise this section, then when I play the video of what to do in EPANET, you'll want to follow along in EPANET 2 and do the steps with me. In this application, we'll analyze this simple distribution network shown here. It consists of a source reservoir from which water is pumped into the simple two-looped pipe network. There is also a pipe leading to a tank that floats on the system. The ID labels for the various components are shown in the figure. Our first task is to create a new project in EPANET and make sure that certain default options are selected. In the defaults window shown in the figures, we'll set the choice of flow units to GPM. This implies US customary units will be used for all other quantities as well. So length is in feet, pipe diameter is in inches, pressure in PSI, and so on. Also, we will choose Heisen-Williams. It's abbreviated in the dropdown as H-W. We'll choose that for the head loss formula. And then under the ID labels tab, we will tell EPANET to automatically label new objects as they are added to the network with consecutive numbers starting from 1. And make sure all the ID prefix fields are empty and that the ID increment is set to 1. Now I'll show a short video of how to do this. Try to follow along and do it yourself in EPANET.
To start a new project in EPANET, let's launch EPANET, go to File, New. We could have also clicked the New button on this toolbar. Now, let's open the Defaults window by going to Project and choosing Defaults. Let's go to the Hydraulics tab and set flow units to GPM and set the formula to HW. Now, let's go back to the Hydraulics tab. Make sure all the ID prefix fields are cleared and that the ID increment is set to 1. We can check this box to save these defaults for all future projects. Let's just click OK now.
Okay, hopefully you followed along there. Next, we will select some map display options so that as we add objects to the map, we will see their ID labels and symbols displayed. In the map options window, under the notation page, check the boxes to display node IDs and display link IDs, like the top figure shows. Then in the symbols page, make sure all the boxes are checked. We'll also double check the map scale settings in the map dimensions window. Just take note of the default dimensions assigned for a new project. These dimensions are fine for this example, so we'll just click OK and we won't change anything. And now I'll show you a short video of how to do this. And again, try to follow along in EPANET.
Now, let's open the Map Options window by going to View and going all the way down to Options at the bottom of the list. Let's go to the Notations page here and check the box for Display Node IDs and display link IDs. Then go to the symbols page and just make sure all these boxes are checked. Then click OK. Now, let's double check our map dimensions before we start drawing the network. We go to View again and choose Dimensions at the very top of the list. Note the default size and the default units. This will work for our map, so we click OK.
Okay. We are now ready to begin drawing our network by making use of the map toolbar shown. We'll start by adding the reservoir, then all 6 junctions, and finally the tank. Don't worry about making all of your nodes square with each other like the figure. Just get them to look similar to it. It won't affect the simulation at all, and we'll be able to use the property editor later to manually set the coordinates to straighten them out. After placing all the nodes, the network map should look something like the figures here. Now, again, another short video, and try to follow along in EPANET.
Now that we are ready to start drawing the network, let's place the nodes. We'll start with the reservoir. So click the Add Reservoir button here. Then click somewhere in the top left area of the network map to place the reservoir. Let's go here. Now let's add the junctions. So click the Add Junction button. We'll try to keep the network fairly square so that it resembles the figures we're referencing, but it won't affect our simulations. Let's place junction 2 here, directly to the right of the reservoir. And let's go junction 3 here, keeping it in line. Junction 4 goes directly below junction 3. And junction 5, again, goes directly below in line. Let's place junction 6 to the right of junction 4. And junction 7 will go directly above junction 6 that we just placed into the right of junction 3 here. Lastly, we'll add the tank. So click the Add Tank button and place it directly to the right of junction 7 here.
Okay. Next, we will add the pipes. We'll begin with pipe 1, connecting nodes 2 to node 3, and repeat for pipes 2 through 7. Pipe 8 is curved, so it will be drawn slightly differently. After the pipes, we will add the pump. And now I'll show a short video of how to do this, and again, follow along in EPANET.
Now, let's add links to our network. First, we'll click the Add Pipe button, which is here. Pipe 1 will connect nodes 2 and node 3. So first, we click on node 2, and note how the outline of the pipe follows the cursor. We'll finish the pipe by clicking on node 3. And pipe 1 is made. Pipe 2 connects nodes 3 and nodes 7. Pipe 3 will connect node 3 to node 4. Pipe 4 connects node 4 to node 6. Pipe 5 will connect node 6 to node 7. Pipe 6 will connect node 7 to the tank here. Then back down here, pipe 7 will connect node 4 to node 5. And pipe 8 is curved, and it connects nodes 6 and 5. To start this, we'll click on node 6. And we just click on where we want the vertice to make the curve. And we keep going. And then we click on node 5 to finish the curved pipe. There we have a curved pipe. Now we will add the pump to the system. Use the Add Pump button up here, and it will connect to the reservoir. So click that first.
Okay, next we will label the reservoir, pump, and tank. Using the Add Text button on the map toolbar, we'll label the reservoir, node 1, as source, the pump as pump, and the tank as tank. You can see the added labels in the figure here. And now I'll show a short video of how to do this and try to follow along yourself in EPANET.
Now we can label our network. Let's click the Add Text button located here. And then we click above the reservoir, and then the box will appear. Let's type in source, and we have to hit enter to finish the edit box. Now let's label the pump, and hit enter. And do the same for tank, labeling it tank. Enter. Now we want to make sure that we click the select object button again, just right here. This way we don't accidentally add more labels when we click into the network map again.
Okay. As objects are added to a project, they are assigned a default set of properties. To change the value of a specific property for an object, we must use its property editor. There are several different ways to open the property editor. Whenever the property editor has the focus, you can press the F1 key and EPANET's help window will open to a page that describes each of the properties listed. If your network doesn't look square enough for you, this property editor is also where you can change the X and Y coordinates. Property editor, don't worry about changing them right now. Again, they don't affect the simulation at all. Two nodes that are, say, 500 coordinates apart could very well as be 1 foot away or 1,000 miles away. It only depends on what the pipe's length is set to. And now I'll show a short video and try to follow along in EPANET.
There are a few ways to open the property editor. One way is to double click an object in the map, like this. I double clicked the tank, and the tank's property editor popped up. Another way is to right click on an object and select properties from the pop-up menu. And now I have the type property editor. You can also go into the data browser and find the object there. So let's go to type 4, select that object, and then you click the edit button. That will open the property editor. To shorten that, you can also just double click the object you want to open the property editor.
Okay. The ID labels for the various components are shown in the figure and should be shown in yours. The nodes in the network have the characteristics shown in the left table, and the pipe properties are listed in the right table. We'll open the property editors and enter the elevation and base demand for the nodes, then length, diameter, and roughness for the pipes. But all the roughnesses should already be correct, so that's fine. For the reservoir, we'll enter its elevation in the total head field. And for the tank, we'll enter its elevation, but we'll also enter its initial level, maximum level, and diameter. For the pump, we will first create a pump curve, and then we'll assign the pump curve to the pump. And now I'll show you, this video is longer, but I'll show you how to do it and try to follow along in EPANET. I'll have these properties on the side of the screen so you can go at your own pace.
Now it's time to set the properties. I have the tables that were on the previous slide on the side of my screen as reference. Let's start with node 1. Double click it to open the property editor. We can use the mouse and click into the field we want, or change the fields using the arrow keys up and down. The table says it has an elevation of 700 and the demand is non-applicable. A reservoir does not have a field for demand, and the elevation actually goes into the total head field for this. So we'll set total head to 700. And we're good. Now we go to node 2, so we click on junction 2, and the property changes to that. The table says it has an elevation of 700 and a 0 demand. While we're doing only junctions, we can use the page down and page up arrow to change between the components. So I hit page down, and now it's the property editor for junction 3. And according to the table, it has an elevation of 710 and a base demand of 150. Now we can go down, page down to junction 4, an elevation of 700 and a base demand of 150. Page down to junction 5, it's got an elevation of only 650, but a base demand of 200. Page down to junction 6, and then we have an elevation of 700 and a base demand of 150. Page down to junction 6, and there's an elevation of 700 and 0 base demand. Now we can click on the tank, and we have its property editor. It's got an elevation of 830. It does not have a field for demand. We can also set other properties for the tank that were on the previous slide. So let's set the initial level to 3.5. The minimum level of 0 is fine. The maximum level of 20 is fine. And a diameter of 60 is set. Now that's all the properties we need to set for the nodes. So let's go to pipe 1, our first link. And we can set the length to 3,000, as the table shows here, the diameter of 14 inches, and a roughness of 100. The roughness is the C factor used in the Heisenbergian calculations. Now we can page down to pipe 2, set the length to 5,000, the diameter to 12, and the roughness to 100. Page down. And for pipe 3, we set the length to 5,000, the diameter to 8, and the roughness to 100. Page down to pipe 4, and it's also got a length of 5,000 and a diameter of 8 and a roughness of 100. Page down to node or link pipe 5. It's also got a length of 5,000, a diameter of 8, and a roughness of 100. Page down again to the pipe 6, and it's got a length of 7,000 instead of 5,000, a diameter of 10 inches, and roughness of 100. Let's page down again to pipe 7, which is down here now. And we set the length to 5,000, the diameter to only 6 inches, and the roughness to 100. And page down, and we're on pipe 8, the curved link, and that has a length of 7,000, a diameter of 6 inches, and a roughness of 100. Now, we didn't set anything for this pump. The pump, you can open it up. The pump does not have a length. It's simulated to have a 0 length. But we do need to set the pump curve. So we go to, in the data browser, we go to down to curves, and we click new. Curve ID 1, that's perfectly fine because this is the only curve in the model. In this table, we set flow to 600 GPM, extend ahead to 150 feet. And here we see EPANET made a complete curve off that one point, and the equation is shown here. This looks good, so we hit OK. Now we can go back and the pump's property editor, and we can set the pump curve to 1. And now the pump will use the pump curve we just made. Let's close this, and we are good for setting properties.
Okay. Now
Hi,
that we've
Benjamin.
made,
Sorry,
yeah,
let's have a quick knowledge check poll, or
sure.
more of a fun question, I guess. We would like to know if you have attended this workshop before. All right, thanks, Benjamin. Back to you.
Okay. Now that we've made the model, it's a good idea to save our work. Let's name this tutorial.net because we'll use this model in the next application. The .NET extension formats the file in a special binary format that keeps everything ordered in EPANET, but most other programs can't read it. Alternatively, we could export the model as an INP file, which is plain text. This is useful for third-party programs to read and edit the model. But now I'll show you a short video of how to save your model, and make sure to do it yourself in EPANET.
Now that we've built the network, let's save it. We'll go to File and choose Save As. Now we navigate to the folder where we want to save the file. I'll use the examples folder that EPANET already made. Here we type in what we want to save it as. Let's save this file as tutorial.net. If we don't add the .NET, EPANET will add it for us. Then we hit save, and our file is saved. Note we can see the file name at the top of the EPANET window.
Okay. We now have enough information to run a single period or snapshot demand-dependent hydraulic analysis on our network. If the run was unsuccessful, then a status report window will appear indicating what the problem was. If it ran successfully, like it should, you can view the computed results in a variety of ways. The first way we'll try is by using the map animation. Now I'll show you a short video of how to do that map animation and try to follow along.
Now we can run the simulation and analyze the results. To run the simulation, we can click this Run button in the toolbar that looks like a lightning bolt, or we can
Let it stop.
go to Project,
Sorry, I don't know why it stopped.
Run button in the toolbar that looks like a lightning bolt, or we can go to Project and choose Run Analysis. After it runs, a box should appear like this. It's saying that the run was successful. If something went wrong, it will say error occurred and will show a status report. So click OK. Now let's look at a way to analyze the results. We can go to the map browser here and choose from the drop down here any of the properties for the nodes. We could do the same for links. Right now, let's just choose pressure for the nodes. Now, see how the nodes in the map area are now color coded. If we want to change the bounds or colors, we can open the legend editor interval bounds, but right now we don't need any of this, so we can just hit OK.
Okay. Now we'll view the results of a component using the property editor. You can note how the computed results are displayed at the end of the property list. We can also create a tabular listing of the results. Now I'll show a short video of how to do both of these. Try to follow along and see for yourself.
There's a few more ways to analyze your results. We could use the graph button here, but there's not a whole lot to see in a graph with such a small network that is also a single period simulation. We can open the property editor for any of these components, and if we scroll at the bottom, these tinted properties that are also in blue, we can't edit them. These are the simulation results, and we can see them for any of the components in the system. If this was an extended period simulation, we could change the results shown here using the map browser's controls down here. We could also make a table by going up here to the table button, choosing what type of table we want to show. Let's choose network links, and it's at hour 0 because again, it's a single period simulation. In the columns tab, we can check which properties we want shown in the table. The ones that are already checked or not are fine, so we can click OK. Now we have a table of the links in the system. Note, some of these have a negative flow. That's because the water is flowing the opposite way through the pipe. That's okay, that's acceptable.
Okay. And now we're at the end of this application, and it's time for another quick knowledge check. True or false, junctions must be placed at the exact coordinates or distance from each other to simulate the pipe lengths. True or false? Okay. The correct answer was false. The pipe length is solely dependent on the length value in the pipe's property editor. And now we'll go to the next application because that was exactly a half hour. Now that we have the model built, we'll use it in some hydraulic modeling applications. For this and the following applications, I'll first describe each step of the application and then demonstrate each step separately. And at the end of the section, there are exercises where you follow the steps yourself and do the hands-on exercises using EPANET. So again, don't worry anymore about copying the video while it's playing. Just pay attention to it so you'll know what to do later. Here are the basic steps to run a hydraulic simulation after having built the model. Each component needs properties set through its property editor. These values and properties depend on the system and the type of simulation. Each simulation needs a total duration set in the time options to determine if this is a SPS, single period simulation, or else how long the EPS will cover. In models for extended period simulations, patterns can be, and commonly are, used to show changes that repeat over a set time period. Typically 1 day or 1 week, but it can be anything. Some, but not all, models need controls to set to show potentially irregular changes in the system. To shorten the simulation duration until the system reaches steady state, we could set some initial conditions, but that's optional. We don't have to. Once we do these steps, we can just run the model and analyze the results. Okay. After opening a model, we can set the time options, namely the total duration and pattern time step. In the exercise, we'll set a total duration of 72 and a pattern time step of 6. The total duration determines the length of the simulation. The pattern time step determines how long each multiplier in the pattern lasts. And now I'll show a short video of how to do this. And again, you don't have to follow along the video anymore. Just pay attention and do the steps in the exercises later.
To set the time options, we go to the data browser and we choose options from the drop-down list. Here, we double-click on times to open the time options window. In here, we can set several parameters, including the total duration and the pattern time step. Once you set what you need, we can close the window.
Okay, real quick. Okay, now patterns are an easy way in EPANET to describe regular changes in the system. We'll create a new pattern during the exercise. We'll make a very simple pattern with only 4 multipliers, and each multiplier covers 6 hours of a daily pattern. In the multiplier row, we'll enter each of the multipliers under the corresponding time periods. We can leave the pattern ID as 1 since this is the only pattern in the model. We won't confuse it with something else. Afterwards, we'll open each junction property and assign them demand pattern 1. Now I'll show you a short video of how to make this pattern.
To create a new pattern, we go to the data browser and we choose patterns from the drop-down list. Now to create a new one, we click the Add button. In the property editor, we can assign the name of the pattern, and optionally we can set a short description for it. In this table, we set the multipliers for the table for each time period. Down here is a graphic that has several key pieces of information for the pattern. This blue line is the average. Typically, we keep that at 1, so that when we assign a pattern to a junction, the base demand of that junction can just be the average demand. Here, we can see that each time period lasts 6 hours. This is because we set the time period or the pattern time step to 6 in the time options. We set 4 of these so that it lasts 24 hours, 1 day, and will repeat daily. And obviously, these show you what level that the multipliers are set to. Once you have your pattern set, you can click OK. Now, once you have created a pattern, we can assign it to junctions. Open up the junctions property editor and scroll down to demand pattern. Here, you assign the pattern ID, the name that we gave it. In this case, it was 1. And now, this junction 2 will use pattern 1 that we just made. And you can go ahead and assign this pattern to all of the junctions.
Okay. EPANET by default performs demand-dependent analysis, DDA, which is computationally easier than pressure-dependent analysis, but less realistic. The demand model can be changed to PDA in the hydraulics options. PDA requires some extra properties to be set in the hydraulics options. Obviously, it requires changing the demand model to PDA instead of DDA. But there's also the minimum pressure, which is the pressure below which no demand can be delivered. There's the required pressure, which is the pressure required to supply a node's full demand. what the requested demand. And to avoid numerical issues, these two must be at least 0.1 psi or meters above the minimum pressure. And then there's the pressure exponent, which is the power to which the pressure is raised when computing the demand delivered to a node. It was suggested to keep the value at 0.5, but you can change it for your system.
To change between demand-dependent analysis and pressure-dependent analysis, we go to the data browser, and we go back to options, and this time we go to hydraulic options. In the hydraulics options window, we scroll down to the demand model. In this drop-down list, we can switch between demand-dependent analysis, DDA, and pressure-dependent analysis, PDA. With pressure-dependent analysis, we need to set the minimum pressure, required pressure, and pressure exponent. Once you've changed the demand model and set the new parameters that it requires, you can close the hydraulics options.
Okay. After running the hydraulic EPS, it's time to analyze the results. We'll create a time series showing the head in the tank, node 8, over the duration of the simulation. And now I'll show a short video of how to create that graph.
After running an extended period simulation, we can find a new way to analyze our results. We can create a graph. Go to the graph button on the toolbar. This will open a graph selection window. Here we can choose what type of graph we'll make. We'll choose whether we'll use nodes or links. We can set the parameter. Depending on the type, you can also set the time period. But a time series like this will show all the time periods, so that's not necessary. Over here, we can add another component. We can rearrange the order that it'll show on the graph, or we can delete the components that we don't want shown on the graph. Once we have this set, we click OK, and the graph is made. This is a time series plot for the head of node 8.
Okay. Another way to analyze the results is by looking at the table instead of a graph. Choose the desired type of table. In the exercise, it'll say to bubble time series for node and to type 5 in the box so that the table will be a time series for node 5. And now I'll show a short video of how to do this, as well as explain some of the optional settings in the table selection window.
Another way we can analyze our results is by creating a table. We can go to the table button in the toolbar, and this will open the table selection window. First, we choose what type of table we want to make. Then we choose either the time step the table will show or the component ID the table will show. And we can create a table just from this, but there are other tabs to refine what the table will show. In the columns tab, we can toggle which properties are shown in the table. We'll take quality off because this is just a hydraulic simulation, so there's no quality to be shown. Here in the filters tab, we can create rules to show what is removed from the table to reduce the clutter, make it easier to analyze. For example, if we go to head and we click add. Now there's a filter that will only show the time steps for our component when its head is above 835 feet. Once we have our table how we want it, we click OK, and the table is created. You can see there's no quality column. Check that off. We can see the demand and pressure from node 8. first time step is actually 3. That is because apparently time 0, 1, and 2 add a head less than 835. We can see time 3 is just above it. So once we have your table, you can find whatever you want from it, but we can just close this.
Okay. And now we're to the hydraulic modeling exercise. These exercise slides have step-by-step instructions for you to follow and do in EPANET. The steps are like what we just showed in the demonstration section. We'll leave the slides up on the screen for a few minutes each, so you can reference the steps while following them in EPANET. And after each exercise, we'll briefly cover the results that you should have seen. So now that I've shown you each of these steps separately, I'll give you about 3 minutes or so to follow these steps to try it yourself. Start with the tutorial.net and model the tutorial.net model, which we built in the last application. It was supposed to also be a handout, but it appears we had technical difficulties making the file models a handout. So take a few minutes to do this. Think about 1 more minute on these instructions, and then we'll move to the results. Okay, hopefully everyone was able to follow these steps, and these are the results. This is what your time series graph of the head for node 8 should look like. The double peak that repeats daily is caused by the pattern. Do you think this looks like the tank has reached an equilibrium? Or does the head stop increasing with each pattern iteration? We can see it hasn't, because if we compare the same point in the pattern's shape for each iteration, it is higher than the previous day. If we want to see how the tank operates in normal circumstances, we'd have to run the simulation longer until it stops increasing daily. Once the head stops increasing each day, it has reached what we call cyclic equilibrium. This is just a more specific term for steady state. We can see it's going, like if we compare this point, 24 hours later, it's higher and higher and higher still, and it keeps increasing. So it hasn't reached it yet. So now let's take the EPS hydraulic model you just made and observe the effects of adding a simple initial condition to this simulation. I'll give you a couple minutes to follow these steps. If you have questions, if we're going a little too fast, I'm trying to slow down, but you can add your questions in the Q&A thing, and we'll try to help you. Just a couple minutes.
And quickly, we are going to launch one more poll.
Okay.
We would like to know, are you attending other sessions during this workshop? Great, thank you for your participation.
About one more minute, or well, I guess you had to answer poll, so we'll restart the 2 minutes. About one more minute. Okay, hopefully you've been able to follow along. We'll go to next, see the results. Here are the graphs from both the simulations you just ran. It's done in Excel because you can't keep graphs in EPANET from previous simulations, because EPANET will just update the graph with the most recent simulations results. This is what it would look like if you could overlay the extended time series graphs that we had you make. for the head of node 8 before and after changing the tank 8's initial level. We can see that when using the default initial level, the blue line, that was 3.5 feet, it took the tank at least a couple of weeks before it reached a cyclic equilibrium or steady state, and it stopped increasing daily then. After improving the tank's initial level, the orange line, when we changed it to should be about 6, it was almost immediately in cyclic equilibrium. This means that we could have ran this simulation for just a few days instead of a few weeks and learned the same stuff. If this was a larger model, like a real city's water distribution network, this difference in simulation durations would be very noticeable in the simulation's runtime. So now that we've done the normal extended period simulation and improved the initial conditions, we'll try a pressure-dependent analysis simulation. I'll give you a couple more minutes to follow these steps, and then we'll go to the results. Got another minute. Okay, hopefully you've been able to follow these instructions and get the same results we'll talk about now. Here are the tables from both the simulations you just ran. Like the graphs, you can't keep tables in EPANET from previous simulations. You probably noticed that after you changed the model to a PDA and ran the simulation, you didn't get the warnings anymore. We can see the left table, which is a demand-dependent analysis, the first one you ran, that demands are always met fully, but the pressures required to meet those demands end up being negative, which isn't really possible in reality. In the right table, though, we can see that all the pressures are positive and then the nodes receive only partial demands. This is more realistic, but even though it probably wasn't noticeable with this small of a system, it increases the simulation run times because it's more computationally heavy. Okay. And now it's time for, we're at the end of the hydraulic application section, and it's time for another knowledge check. So fill in the blank. EPANET can use a blank-driven or blank-driven approach to solving hydraulic simulations. Okay. The correct answer was pressure and demand. EPANET can solve hydraulic simulations using a demand-driven approach, DDA, to compute pressures and flows, or a pressure-driven approach, PDA, if these are pressure-deficient conditions. Hopefully most of you got that right from what we just had you do. And now we'll go from the hydraulic modeling to our first water quality modeling, which is water age. Because water age is not an explicit water quality, it's most useful as a general indicator of the overall water quality and is usable in systems no matter what disinfectants are being used. Because it's easier to make changes to a model than a system, water quality modeling is commonly used to estimate the effects of water quality from potential design or operation changes. Simulations are a great way to analyze the results of a change in the system. Water age is particularly useful when testing changes to a tank because tanks are often a major cause of higher water age. Water age is also good to see the effects from a model that has been skeletonized. Skeletonization typically removes smaller pipes, which are more than often dead-end pipes and branches of a system. A skeletonized model typically reduces the water age, and you can get an idea of how less accurate the model is by how much the water age drops. Okay. Recall that running a water quality simulation requires an EPS because it takes time to reach an equilibrium state, especially since most systems have demands that change over time. It's relatively simple to take a hydraulic model and turn it into a water age model. Set the time options, namely the total duration, so it's an EPS, and the quality time step, though the default value of 5 minutes is usually fine. Set the quality options parameters to age so that the water age will be simulated. If it's not already set from the hydraulic model, set the most representative mixing model for each tank. And some initial conditions can also be set to shorten the simulation until a steady state is reached, but it's not required to run the simulation. Then we just run the model and analyze the results. So in the time options window, we can enter a value for the total duration. We'll use a total duration of 240 or 10 days and report start time of 168 or 7 days. This way, the results will only show day 7 through 10, and we won't see as much of the approach to a cyclic state, cyclic equilibrium. We'll keep the quality time step as the default 5 minutes, and now I'll show you a short video of how to do this.
To set the time options, we go to the data browser, we go to options from the drop-down list. We double-click on times. In the time options, among other parameters, we can set the total duration and the reporting start time. Setting the report start time is a good way to remove the transient state from the analysis. Once we set what we need, then we can close time options.
Okay, that should look pretty familiar. But now in the quality options window, we'll set the parameter to be modeled from the drop-down list of chemical trace or age. In this case, we'll want to choose age to model the water age. And now a short video of how to choose this.
To make this a water age model, we go to quality options, which is still under options in the data browser. In the quality options window, we choose the parameter from the drop-down list. To be water age, we want it to be age. Once we have that set, we can close the quality options. This is now a water age model.
Okay. We can choose the tank's mixing model from the drop-down list in the property editor. Our first exercise will use mixed for the tanks mixing model, but we'll also test out FIFO and LIFO during the second exercise. We explained the different mixing models in the lecture part of this workshop, so before lunch. It was back on slide 57-ish. And now I'll show a short video of how to change the mixing model.
To set the tanks mixing model, we need to go to the property editor. Open that. Then we scroll just over halfway down until we get to the mixing model property. We click on it and we're given a drop-down list. Here we can choose which mixing model we want. You select it, and then you can just close the property editor, and your tank is set to that mixing model.
After running the simulation, we'll use the map animation to analyze the results. We obviously want to analyze water age, so we'll set the nodes in the map browser to age. Then we can set the ramp steps in the legend by right-clicking on the legend to open the legend editor and entering the values we will want. Setting the intervals for every 25 hours is very simple, but it's also pretty reasonable for water age, because typically small systems have an average water age between 24 and 88 hours, 1 day and 3.7 days. This will mean that dark blue nodes will have a great below average water age, that light blue and green nodes have a typical age, that yellow is a still okay age, but might be pushing it, and red nodes have notably high water ages. After the legend is set, we can control the animation with the controls at the bottom of the map browser. I'll show a short video of how to do these.
To use the map animation, we first need to run the simulation. After that, we go to the map browser. We set what property we want to show for the nodes. In this case, we'll do one age. We won't worry about links. Once you set that, the legend appears. We can right-click on that to set the bounds, to change the bounds for each color. Just go something simple. Okay. You can also use some of the preset to change the bounds or change the colors to reversing colors. Once you have that set, you can click OK. Now over here, we can use these controls to change what's shown in the animation or play the animation. This slider changes the speed that the time step change. So we'll go play. See the time's changing, colors are changing. You can speed that up. We can stop the animation. You can go back to the beginning. We can just manually choose which time step we want to show. That's how you control the animation.
Okay, and that's it for the demonstration. I think this is the time for one of our fun polls.
Yes, that would be great. Thanks, Benjamin. Our question for you is if you have questions for our speakers. If you do, please type them in the chat box or in the question box, excuse me, and we will get to it during Q&A. All right, back to you, Benjamin. Thank you.
Okay. Thank you. So now, using what I just showed you, take 3 minutes or so to follow these steps and do it yourself. And then we'll switch to the second water age exercise because they're all related, and I'll show the results of both of them together. This says to use Net1, which is an example network that was included in the EPANET 2.2 download. You can find it in the folder called example in your EPANET folder. So about 3 minutes now. Just under a minute left. Okay, hopefully we're able to follow these instructions, and I will go to the next exercise, which is more like a part 2 of this. And I'll give you 3 more minutes to follow this exercise. And then we'll look at the time series graph of the tank's water age using the different mixing models, all 3 of them overlaid. See if you can come up to the same conclusion using the map animation as we'll see with the time series. Okay, we'll take about 1 more minute. Okay, hopefully you've been able to follow these. And now that you've used the map animation to compare the water age and the tank using different mixing models, let's look at what the water age actually was in the tank. The animation just gave a bounded estimate with each color. The mixed mixing model was the steadiest, and except for a single time step at hour 219, the tank should have stayed the same color at yellow. This was the blue line here. FIFO, first in, first out, had some dramatic spikes and was normally higher than mixed. You should have seen it alternate between red and yellow once a day. LIFO, last in, first out, had significantly lower water ages and should have alternated daily between dark blue and cyan. The mixing model should be chosen to reflect, note though, the mixing model should be chosen to reflect how your physical tank is designed and operated. This exercise just shows how different types of tanks affect the system differently. Unfortunately, changing the mixing model in your model doesn't magically improve your physical system. That'd be awesome if it did though. And now we're at the end of the water age application section. Just one more application to go, but now it's time for another knowledge check. Which of these does not affect water age? Okay, see, most of us got it right. Correct answer was levels of disinfectant. Water age is a surrogate of water quality. So while water age may suggest a change in disinfectant levels, a change in disinfectant levels does not change the water age. So now it's time for our last application, chlorine modeling. Chlorine modeling is commonly used and has many different application uses. Like water age, it can simulate the effects from adding or removing components like tanks, but the effects are only for the modeled disinfectant. Chlorine modeling can show areas with lower than acceptable concentrations and can help find the best locations to add booster stations. Chlorine modeling can chlorine modeling can show the effects of changing the source feed concentrations, the concentration at the reservoirs in this case, or changing the disinfectant type. Unlike water age, it is also used for hindcasting. You can set the model up as it was in a certain scenario and simulate what happened and figure out how and why that happened. This is useful for recreating complaints, like a customer's tap smelled more strongly of chlorine or something. And in litigation cases, chlorine modeling can help determine if something in the system was not meeting the legal requirements. There are some common factors that majorly affect chlorine in water distribution systems. The source water quality, like a reservoir's initial quality and source quality in EPANET, is a major influence and should be obvious because it represents how much disinfectant you're adding to the treatment plant. The general operation of the system, when tanks and pumps operate, when there is higher or lower demands, or when pipes are closed or open, all influence the system. Transport in the distribution is also a factor, like whether the system is looped or branched or has many low flow or dead end pipes. Transformations of the disinfectant is another factor. Mostly it's reaction values chosen to simulate the disinfectant, but those values are dependent on everything from the pipe material and age to the type of disinfectant being used and the natural contaminants in the water. Storage, mostly through tanks, is a huge factor for chlorine disinfectant because the water often sits in tanks for long periods if the tanks operate that way. And it's not always mixed in the tank either, it can sit stagnant. Setting initial conditions, like chlorine concentrations in the model, is an optional step, but can be very beneficial, especially at reservoirs and tanks that can take very long times to reach equilibrium. Setting initial conditions can reduce the necessary simulation durations and therefore simulation runtimes to just a fraction of what would be required if you didn't set the initial conditions. Changing a hydraulic model to a chlorine model involves a few more steps than changing it to a water age model, namely setting all the reaction values. You still set the time options, like choose the total duration, so it's an EPS simulation, and check the quality time step. The default value of 5 is usually fine though, but it depends on your simulation. Set the quality options parameter to chemical so that a chemical with the set parameters will be simulated. Defining the reaction parameters for chlorine is an important step, and the values vary for different systems. If it's not already set from the hydraulic model, you also set the mixing model for each tank, which I think we're familiar with now. We can still set some initial conditions, like chlorine concentrations, to shorten the simulation time until a cyclic equilibrium or steady state is reached, but it's not required to run the simulation. Once everything's set, you just run the model and analyze the results. In the quality options window, select the parameter to be modeled from the drop-down list. In this case, we'll obviously want to choose chemical. Still in the quality options window, we can select the mass units from the pull-down list and decide between milligrams per liter or micrograms per liter. Sorry, we'll keep it at milligrams per liter, mg/L. And now I'll show a short video of how to do this.
To set the water quality, we go to the data browser. From the drop-down list, we choose options, and we double-click quality. In the quality options window, we choose the water quality by choosing the parameter. From this drop-down list, we'll choose chemical to model chlorine. Depending on the chemical, we can also change the mass units, but this is fine for chlorine. And once we have this set, we can close the quality options.
Nice and short. Now, in the reaction options, we can set the reaction rates for the chemical being tested. For conservative chemicals, just enter 0 for both the global bulk and wall coefficients. Usually that's the default value. For non-conservative chemicals, like chlorine that we're going to be modeling, values must be entered for several properties. In the reaction options window, 2 properties must be chosen to define the bulk reactions. For the bulk reactions order, typically a value of 0, 1, or 2 is used, and chlorine usually uses 1. Then enter a value for the global bulk coefficient. Remember to use the negative coefficient value for decay. Bulk coefficient values typically range between negative 0.2 and negative 1 for chlorine decay. For chlorine, in the exercise, we'll use a negative 0.5 for the global bulk coefficient. Now I'll show a short video of setting these.
To set the reactions of the chemical being modeled, chlorine, we'll double-click reactions, still under option in the data browser. This opens the reactions options window. We need to set the bulk reaction order, which is usually 1 for chlorine, and the global bulk coefficient, which has to be a negative number to model chlorine decay, but it can be a number. Once we have this set, that's all we need to model the basic chlorine decay.
Okay. For wall reactions, several properties can be chosen in the reaction options. A value of 0 or first is chosen from the drop-down list for the wall reaction order, and a value is entered for the global wall coefficient. Instead of setting the global wall coefficient, you could set the wall coefficient correlation value, but we won't worry about that in the exercise. When we model chlorine decay at the wall, we'll use a first order reaction and a coefficient of negative 1. And now I'll show a short video of setting these.
We can make this chlorine modeling a bit more advanced by adding in the wall reactions parameters. Still in the reactions options window, we can set the wall reaction order, which chlorine will be first, and the global wall coefficient, which again has to be a negative number to model chlorine decay. Alternatively, we could have set the wall coefficient correlation, but we won't worry about that in the exercises coming up. So once this is set, we can close the reactions options window.
Okay. Source concentrations are usually defined at reservoirs representing water entering the distribution system, such as from treatment plants, wells, or transfers. The values set for the initial or source quality are in mass units set in the quality options. So in our case, an initial quality of 1 means chlorine concentration is 1 milligrams per liter. If the source quality is constant over time, then the easiest way to enter the value is as the initial constant concentration at the reservoir. If the concentration changes over time, then click on the source quality box, and that will bring up a dialog box shown here. Here you can enter the source quality and a time pattern showing how that quality changes over time. Now I'll show a short video of how to set this. We'll only be using the initial quality in the exercise, so the source quality is just extra information.
While modeling chlorine, it's important to set the source concentrations. In the reservoirs property editor, we can set the initial quality right here. If the source quality is set, like it's not set here, the simulation will continue to use the initial quality throughout the simulation. Alternatively, we could set the source quality and have the quality change with the pattern, usually throughout the day. And we have different options or how it's measured and whatnot. But we won't worry about that in the exercise coming up. With the initial quality set, we can close the reservoirs property editor.
Okay, and that's the end of the demonstration section, so it's time for another poll.
Thanks, Benjamin. We would like you to rate your current understanding on the session topic, please.
Okay. And now we're to the step-by-step exercises again. Now that you've got some experience from the other exercises, and I just showed you the steps for chlorine modeling, let's have you follow these steps and model chlorine firsthand. I'll give you a few minutes for before moving to the next exercise. Well, I'll show the results first. If you didn't save the file back in the hydraulics exercise, it was supposed to be available in the handouts. So hopefully you saved tutorials I1. Just give you a few minutes. About one more minute. Okay, hopefully you've been able to follow these steps, and now we're going to review results. So the exercise showed using nodes 3, 4, and 5. Each of those are increasingly farther away from the reservoir. And now, how does that distance affect the chlorine concentrations? You can see that the farther away the node is, the longer it takes to reach a steady state. The farther away a node is from the chlorine source, in this case the reservoir, the lower the chlorine concentration, because the chlorine reacted in the bulk water as the water was being transported to the network. So we can see node 4 is less than node 3, which was closer, and same with node 5. And now it's time for the last exercise of this workshop. I'll give you 3 more minutes while you add in the wall reaction to the simulation. And then I'll go over the results. About 1 more minute or so. Okay, hopefully you've been able to follow these steps. And now we'll switch over to the results and see what adding in the wall reaction, what happened with that. Now, how did adding the wall reaction change chlorine concentrations? Each of the nodes' chlorine concentrations decreased significantly from adding the wall reaction. Node 3 dropped from 0.99 to 0.92. Node 4 dropped from averaging about 0.97 to about 0.75. I mean, it changes, but that's average. Node 5 similarly dropped even more. It went less than half of it. Before wall reactions, it averaged 0.9, and now it's down to just 0.43. So the distance is an even larger factor when the wall reaction is also considered. Now we're at the end of our last application, and it's time again for a knowledge check. Typically within what range is the global bulk coefficient for modeling chlorine decay? Think about what we set in the last exercise, well, 2 exercises ago. Okay. Negative 0.2 and -1 was the correct answer. The other units were wrong, and it has to be a negative number to show that it's decay. So now we're to the closing, and I think Rob is going to take over here.
Okay, thanks, Ben. At this point, hey, Ben, how about we just continue showing your screen, if you don't mind?
Yeah, I didn't tell it to stop.
Okay, so let me change this. So we wanted to just reiterate for everyone that there's a few places you can go to get help. One is our US EPA website. And if you have questions on running EPANet or downloading or any technical questions you may have or problems you may have with the software, you can email us at epanet@epa.gov. You can also go to our US EPA GitHub site for EPANet 2.2, which is shown here on the slide. It's also, this link is also on the webpage. And you can also go to the EPANet community at Open Water Analytics. Specifically questions dealing with the hydraulic and water quality engines. This is probably the best place to go. And the link to that wiki for questions is shown here on the screen. And there's also a community forum. You can post questions there. And we also want to reiterate that if you want to become a contributor to EPANet from a programming standpoint, or actually if you just want to contribute by raising issues or pointing out problems, bugs, if you will, from using EPANet, please go to Open Water Analytics EPANet issues and open an issue and communicate with the community through Open Water Analytics. Next slide. Our contacts for EPANet are also shown here on the screen. The EPANet at epa.gov is a general contact location that we can all get access to, but individually, if you have questions, you can also contact us at these email addresses. Next slide. So I guess we have one final concluding knowledge check. Do you feel like you learned something about EPANet from these from this webinar, this workshop? So if everybody's answered that question, I think we can move on to the question and answer session. And I think John Burkhart's going to lead this. And then we'll each, help John as needed to answer these questions. John?
Yeah, thanks, Rob. So one of the questions that came up during the first hour or so of the sessions was related to, we actually got a couple questions about premise plumbing or facility level modeling. And I'll just answer that generally, and that's something that I'm working on. And the answer is yes, EPANET can be used to model, premise plumbing systems or facility level, modeling. And if you have any questions about that, it's a little obviously beyond this session, but reach out to me. Rob just shared my email, and it's available with the slides. One of the other things, and I'm going to just ask, I know Rob and Tara have been answering questions as they've come in, and if you saw one that was particularly important, please raise that. They're showing up answered at the moment. But I'm just going to start with one that's probably for Feng, and that is plug flow reactor the best approach for modeling chlorine decay in waterline? Also, is this reactor assumption used in EPANET?
Not sure what's the best. Plug flow probably mimic some very long pipe type tank. But in reality, lots of tanks, like I see here, Cincinnati, it's a huge one. I don't think it's very close to plug flow. Two compart with each part complete mixing seems more realistic for me, but I don't have much experience on the field. Yeah, but for plug flow, I would say, which tank, if the tank is work like a plug flow, probably it's very long, huge pipe. This type of tank will work like a plug flow.
Thanks, Feng. Yeah, for actually transporting, the EPANET breaks pipes down into segments, and then it's reacted away with the equations that were shown. So again, if you have specific questions, feel free to send us a question and we can try to answer it. And then let's see, I guess, not sure who would be the best to answer that. Where's the reference for settings needed for boosters with a VFD or variable frequency drive? So if one of my co-presenters wants to field that.
EPANET doesn't have VSP modeling capability. So, but you can try different pump setting to see how it works, or you can use some control if then change the settings. Yeah, I know it's because most commercial software already have VSP. Bentley has a patent on it, but it's not currently in EPANET. But I can,
right.
from trial and error point of view, yeah, you can use some pump setting to see how it works out.
All right. And here's another one probably for you, Feng, as well, or any of us, but can EPANET analyze fire flow?
Yeah, it can, because you can just assign huge demand to nodes and to see how pressure differs. Commercial software has a fire flow analysis module, but it's basically using hydraulic engine of EPANET to do the analysis, to do 100 scenario, simulate a fire flow junction by junction. That's probably most likely what they do. You can do it manually. You can use EPANET toolkit if you can program to simulate a fire flow node by node. So yeah, the basic capability is there, but since EPANET is not a commercial software and we don't have huge amount of developers to developing this kind of add-on modules, so yeah, you probably won't see like 5-flow analysis in the manual like commercial software, but the basic functionality is just hydraulic simulation.
All right, thank you. So there's a few questions that I think may have been answered about, when these the recording of this would be available. I know last year's training is currently available and was on the website that you would have gone to register. I believe last year it took a few weeks to actually compile all the videos and get those online, and I'm assuming that that was answered by one of the organizers. But again, if you're, want to sort of review some of the topics, last year's training, which is a little different, is currently available for review, and hopefully be on the lookout for the recording of this session. I don't know, Tara, I saw you answered a couple interesting ones. Do you recall any that jump out?
Not off the top of my head, but let me review some.
Just trying not to bombard Fung with all of these. There's one on, in chlorine practice, I believe that the wall coefficient is significant given that ductile or cast iron has been used in drinking water distribution systems. Can this be ignored, or is there any good reference for this coefficient?
Yeah, I'm not aware too much. In user manual, EPANET rule basically link the water coefficient to pipe roughness. So it's quite reasonable, and he has some literature reference. If you go to the EPANET manual, you can see that. But in recent years, I didn't notice much related work. So I think if the regulation, requirement, maybe we will see more research on this, because you cannot measure that, and so you can only calibrate it with field data. So you can use bottle test to determine the bulk decay coefficient in the treatment plant or in the lab. Then you plug it into the water quality model, then you run it without water decay coefficient. Then you can see how if it's way off from the field data, it's likely tell you what decay coefficient has to be brought in. Then you can adjust the decay coefficient. You can group pipes into multiple types, maybe cast iron. So you have probably several different work coefficients depending on the material. You can do the calibration. It's involved lots of field work, I would think. But I didn't realize lots of research are done in literature from my experience.
Yeah, thanks, Fung. And this is actually kind of related to a question that Rob answered related to the temperature effect. And this sort of builds on what Fung just said about temperature effect and, conducting a bottle test. So you would, conduct that, and you could incorporate, the temperature into that as well. And so thanks, Rob, for addressing that in the chat.
I think if you really go very deep into what the quality modeling distribution system, probably you have to involve multiple reacting species. So that's research direction, and we are working on operating multi-species extension. But if we use just single species like traditional EPANET, yeah, it's quite hard to, because this water decay coefficient is not a physical, it's just a modeling parameter.
Right, and thanks, Fung. So there's one about that you did answer, Tara. I think this is what I was thinking about. Can you import a CSV file or other table with a node related to GIS, into EPANET from another program? And you provided the answer, but if you want to touch on that again.
Right. So currently, EPANET does not have, or at least our GUI version does not have GIS capabilities. But we do have a kind of beta test prototype that we're working on, trying to get this capability. But we do have some workarounds if people want to try to contact us independently, and we can help you figure out how to get that information in. We've opened up CSV files and kind of copied and pasted those files directly into the EPANET input file that's in the text version of that. The IMP file is what we call it. So there is some workarounds like that, or we have other tools that we use in-house too that can get us around those. But we know that is a huge advantage using some of the commercial softwares, obviously, is the GIS capabilities. So, but we also have to be aware that we're not in competition with the commercial entities, so we kind of have to walk a fine line. But we know that this is a feature that most people would benefit from having that GIS transition to the EPANET. So we're aware of this, and we are trying to work towards a solution.
Great, thanks, Tara. There was another question that Rob fielded on how do you model hydropneumatic tanks. It looks like that was already addressed in the online manual, and Rob kindly provided the link. So if you're interested in modeling that, please take a look at his response. Again, Rob, did you see any others that jump out at you?
No, I'm not seeing. I think we've answered them. I think we've covered them. There are some folks that had trouble keeping up, I think, during the applications. But I think with the recorded presentation and these slides and videos, we should be able to make all this available. It shouldn't be too hard to do this on your own at your leisure.
Yeah, thanks, Rob. And there's a new question, but it reminded me of an older question, which is related to the tank's residence time. And we don't, in EPANET, you don't actually explicitly provide that. You provide the dimensions of the tank, and then in the EPS simulation, it will fill in empty, and that's going to give you your residence time. But the new question is, LIFO mixing showed much lower water age. Does that change dramatically if the tank empties? I don't know, Ben, if you wanted to answer that, or Feng, now that you popped on.
What? I didn't quite get the question. Last first out?
Yeah, so last in, first out mixing showed a much lower water age. Does that change dramatically if the tank empties?
Well, I try to figure out the question. So if last in, first out, then yeah, of course it's, because the first part of the water in the tanker, they stay in the system for a very short time, right? Last in, first out. But it also depends on the size. If it's very large, last in, first out tank, then at a certain, most time if you do the exchange during the very first part, then suddenly at some point, it drains the water in the back end of the pipe. Then you get very high water age water too. So it depends. I don't think you have to analyze case by case, basically.
Yeah, and you're right, Feng. It would be short water age for a while, and then potentially very high, and then when the tank is fully empty, it would be.
You will see dramatic change probably. Sometimes you get very fresh water. Sometimes if lots of water poured out, then you get very old water, because at the back end, water probably never get replaced.
Right. So I think, unless I'm missing anything, I think we've addressed all the questions. So I'm going to hand it back over to Rob to close us out, since we're closing in on the hour.
Well, thank you everybody for attending. Really appreciate it. Like the feedback. It looked like we had quite a few people attending, and we're really happy to see that. And I guess look forward to hopefully doing this again next year. So thanks again to everybody. Thanks for the presenters, and Katie helping us on the organization side for GoToWebinar. And I hope everybody has a great rest of your day.
Thank you.
Thanks everyone for your time.
Bye.
Yes, thank you all for joining this session today, and we hope to see you at our other workshop sessions this week.